class, welcome to the Kinetics and Equilibrium review. As usual, major understandings are in bold and practice questions are below. Let's get started. The first thing we need to consider is the collision theory. The collision theory says chemical reactions only occur if the reactant particles collide with sufficient energy and proper orientation. First, let's look at what we mean by proper orientation. We'll do this by looking at my daughter's Legos. Here you can see two Legos that are properly arranged or oriented to have a combination. So in this case, we can have a chemical reaction. Chemical reactions, the reactants, or what you put into an equation, are separated from the products, or what you get out of an equation. So the products in this case would be a stack of Legos. So here you can see what a typical reaction would look like. Our products are what come out of the reaction. Now, let's take a closer look at what we mean by orientation. If my products were arranged in this way, notice their orientation or their arrangement is not one that is conducive to the Legos sticking together. So in this case, we would have a no reaction. No products would actually form. So in addition to orientation being really important in the collision theory, we also know that energy is also very important. We can see the importance of energy using potential energy diagrams. In these potential energy diagrams, they represent the stored energy, potential energy, sometimes also looked at as heat energy of various reactants and products through the course of a chemical reaction. In the reaction to your left, this reaction is exothermic. We can see that there is a release of energy as the overall reaction is going down. In this exothermic reaction, basically what we know is we have reactants. Let's say in this case it would be a compound, and it is breaking apart, forming products, and releasing energy. So energy is a product. We'd also know that our delta H, our heat of the reaction, which is formally defined as the heat of the products minus the heat of the reactants, is going to be negative. Versus in the reaction to the right, it is an endothermic reaction, meaning heat is absorbed. In this case, we have the reverse situation where heat is a reactant used to cause a chemical reaction. And in this case, our delta H is going to be positive. Now we see that because we can see that the plateaus are increasing, and so heat must be absorbed. And delta H, which is the products minus the reactants, always is going to be positive. Now when we say that chemical reactions only occur if the reacting particles collide with sufficient energy and proper orientation, when we look at the sufficient energy, what we're really referring to is the minimum amount of energy to get the reaction started, labeled E sub A, but called the activation energy. And again, the activation energy always spans from the first plateau to the peak of the potential energy diagram. Now, if you would like to speed up a chemical reaction, what you essentially need to do is speed up collisions. And the major factors that influence the rate or could speed up the rate of a chemical reaction are listed here. Let's take a look and see if we can do a few practice questions. So in question number 1, they ask us about a catalyst. So catalysts, what they do is they speed up chemical reactions by decreasing the activation energy. So if we have an uncatalyzed reaction that has a potential energy diagram, and it could be endo or exothermic, it really doesn't matter, that looks something like this. If I added a catalyst, what it would do is it would provide an alternate pathway for reactant particles to collide with sufficient energy and proper orientation. And so it lowers the activation energy. So here you can see that the activation energy is represented by this red line, which is significantly smaller for the catalyzed reaction than the uncatalyzed reaction. Now please note that catalysts do not affect the potential energy of the reactants, the potential energy of the products in any way. They only, or even the heat of the reaction, which is the products minus the reactants, only affects the activation energy. So basically, again, we have this word catalyst, and it's really important that you understand that it works by decreasing the activation energy. In question number 5, it asks, which 4-gram zinc sample will react the fastest? And here we have different sizes of particles. We can remember that size of particles is related to surface area. And the larger the surface area, the faster the reaction. So basically, the smaller the particle, the larger the surface area, the faster the reaction. So here, the smallest particle size is going to be powdered. Now, as we continue with the same idea, again, the connection, the smaller the particle size, the larger the surface area, the faster the reaction, we get to the next question, which gives us a reaction, and asks the rate of this reaction can be increased by using 5 grams of powdered zinc instead of a 5-gram strip, literally a rectangular piece of zinc, because powdered zinc, smaller particles, has more surface area. Question number 5 asks, what happens to the collisions as temperature increases? We recall that as we increase temperature, we increase kinetic energy. Kelvin temperature is directly related to the average kinetic energy. So as we increase the temperature, the particles move faster and the effective collisions increase, thus increasing the rate. The next big idea we want to look at is the idea of chemical and phase equilibrium. We know that by definition, equilibrium is a situation where the rates of the forward and reverse reaction are equal, while the concentrations of the reactants and products is constant. Remember con-con. This is like a basketball game. Here we have a basketball team with 8 players. There are 5 on the court and 3 on the bench. Now, at any one time, what a coach might do is might pull out a player. So if a coach pulls out a player, the player will come out, but then another player will go in. Now, if things are going quite poorly, the coach may call out 2 players. Then what will happen is the coach may go and have to go and put back into different players. But you can see that it doesn't matter. There's always this movement of players between the court and the bench. But the total number of players on the court is constant. There are always 5 players on the court and 3 players on the bench. Now we know that 5 does not equal 3, but so they're not equal, the concentrations or the numbers of players in each part, but they're constant. There are constantly 5 players on the court, 3 players on the bench, and the rate The amount of players going back and forth is the same with each exchange. So if 3 players come off, then what will happen is 3 players will go back on. Equilibrium is typically denoted with a double-headed arrow. This indicates that the rate of the forward reaction is equal to the rate of the reverse reaction. Lastly, Le Chatelier's principle explains when a system is at equilibrium and a stress is applied, like a change in temperature, concentration, or pressure, the system at equilibrium will shift to relieve that stress. If you've ever had a color-changing toy, you've likely witnessed a reversible chemical reaction that changes its position of equilibrium due to Le Chatelier's principle. So if you have a color-changing Hot Wheel, what likely happens is you actually have a system at chemical equilibrium. And what you have is you have a constant concentration of 2 different colored particles. So notice that we have 6 reactant particles in a red color here and 4 product particles in a blue color. And once this system reaches equilibrium, the reactants will slowly go to form products at the same rate that the products will form reactants. So what you will see is that these reactants will collide and they will go and they will form products at the same rate in which the products are going to collide and form reactants. But remember that once the product or reactant is formed, it's going to have a different color. So the reactants are always red and the products are always blue. So we have this back and forth going all the time, and it's at an equal rate. Now, initially, what happens is at room temperature, let's say, or at this condition, when I look at my car, if I wanted to see what color the car is, it's going to be red. Why is it going to be red? Because there's more red. Now here you can see that this is an endothermic process because we have heat as a reactant. So if I add heat, what I'm going to do is I'm going to cause the particles to collide more often. And since heat is essentially a reactant here, I'm going to cause the reactant particles to collide much more often to form more products. So if that happens, then I'm going to shift equilibrium. When we have Le Chatelier's principle, we can basically think of this system like a seesaw, where the fulcrum is underneath the arrow, and the reactants and products start equal in a very balanced way. Now, if I add something to the reactant side, to the left side, what's going to happen? So in this case, if I increase temperature, it's like adding a reactant, and my seesaw is going to shift in this direction. Le Chatelier's principle always says that we shift towards the upside of the seesaw. In that case, what's going to happen is more reactants will react to form products. So these reactants are going to move to the product side. Let me grab the reacting particles. Going to move to the product side. But remember that once they turn to the product side, they actually become blue. So now we have a shift in the ratio or the number to red to blue. So as we apply heat to what was our red Hot Wheels, our Hot Wheels will turn to the color blue because the equilibrium has shifted towards the product side or towards the blue color. Now, of course, as we decrease the temperature, we let the Hot Wheels cool, then the equilibrium could shift back and our Hot Wheels could return to the original red color.